Rest of today's lecture, we will use SPSS to perform one-way analysis of variance and called ANOVA analysis. And data set we use today is called LEAD, LEAD.SAV. And this data set is used to assess effect of lead exposure on neurological and psychological function in children. A group of children who lived near a lead smelter in El Paso, Texas were identified and their blood level of lead were measured. An exposed group of 46 children were identified who had blood lead levels greater or equal 40 microgram per milliliter in 1972 or 1973. A control group of 78 children was also identified who had blood lead level less than 40 microgram per milliliter. Two important outcome variables that were studied were: 1. The number of finger wrist taps in the dominant hand, and the Wechsler full-scale IT score. And in this analysis, and we are going to use finger wrist taps, number of finger wrist taps for our analysis. So let's go to SPSS. Okay, so this max FWT is a maximum of a finger wrist tap scores. It's a maximum of left or right hands. Okay? And there are three lead type, and if you look at the value, okay, so 1 is coded for group without exposure, 2 is coded for group with current exposure, and 3 is coded for group with the past exposure. Okay, so one-way ANOVA independent variable is a categorical variable, which is lead type, and outcome variable is a continuous variable, which is max FWT. And so those are two analyses we are going to use in today's example. And there are actually several ways and you can perform one-way ANOVA in SPSS. And compare means in one-way ANOVA, this is one way. And although in this lecture we are going to use general linear model, univariate this option. And one-way ANOVA is in fact a form of linear regression. And general linear model is a linear regression, which is actually you have a choice to do linear regression. So it's a little bit confusing. You can do use a different method or tabs to do a same test. Today, particularly, we are going to use general linear model and univariate option. And by the way, univariate is not really the one independent variable. Univariate analysis means analysis in here under GLM. Analysis involves just one outcome variable, and then you can involve many independent variables. Multivariate is for ANOVA which contain more than one dependent variable. Okay? And repeated measures is you have more than one dependent variable based on repeated measures. So these two models are actually similar. Today we are going to do analysis with one dependent variable. So we use univariate option. So when you plot this data and with a box whiskers plot, and it will look this way. So as you see, current and past lead exposure finger wrist tapping score is less than the group of non-exposed. Okay, so let's perform one-way ANOVA analysis. So you go to the general linear model and univariate. Okay. And then you put max FWT under dependent variable and put the lead type under the factor variable. And we will talk more on what is factor and what is covariate and what is random factors. And and for now, okay, and these three boxes are the where you can put the independent variable, but today we put it under the fixed factors, okay, and the factors in SPSS are for categorical variables, and covariates are for continuous independent variables, okay, and I'll explain what the random the last week of this course. So after you put the lead type and then you click the post hoc, okay, and then when you click post hoc, so let me go to SPSS at this point. Okay, so you go to general linear model univariate and put the max SWT under dependent and put the lead type under fixed factors, okay, and before you click post hoc, let's click the model, right, and let's click on custom button and put the lead type under the model, okay, and then click continue. We have only one independent variable, so you don't have to worry about anything else, and click continue, okay, and then you click on post hoc button. So that's where you can specify post hoc pairwise comparisons using Bonferroni and other method. So these are not highlighted. So in order to highlight these, and then you need to put the lead type under this box. So here, LSD, and I'll explain what that is later. LSD you can view as similar to student t-test. So here you have three groups, but you are to compare each of two pairs at a time, not expose current and not expose the past, then current and past using student t-test. It's slightly different, but you can view that as a student t-test. And Bonferroni is a method, and you grab the p-value based on LSD and multiply by total number of comparison, and which multiplied by 3. So let's click both. LSD give you the original p-value without multiplicity adjustment, and then Bonferroni's p-value be multiplied by 3. And Sidak's method, and we talk about it, and you mathematically derive a p-value of the probability of detecting at least one pair being statistically significant. And there are other methods, Dunnett method, if you can click. And Dunnett method, and as we talked, and we compare exposure category to one reference category. So you need to specify what would be a reference category. So here we want to use control as a reference category. So we set this to the first. Okay. And let's click continue. And I think we are all set to click OK. Right. So when you look at this table, and this p-value 0.012 for lead type, and this is a p-value for ANOVA. So what does this mean? When the p-value is less than 0.05, and then you conclude at least one group's outcome is different from another, so therefore you are allowed to look any pairwise. So this is a pairwise. So if you look at the LSD, and it will return a p-value without any multiplicity adjustment, and you compare no exposure to current exposure, and p-value for that is 0.009, and no exposure to past exposure, and p-value for that is 0.056, and then you have current exposure to past exposure, the p-value is 0.619. And then you see 6 p-values for actually 3 pairwise comparisons, because no exposure, current exposure are also repeated as current exposure and non-exposure here. So the p-value of this one and this one is the same. So it's redundant. Okay. So if you look at the Bonferroni p-value, these p-values are multiplied by 3. I think that it's not exactly 0.027 after you multiply 0.009 times 3, but I think that the decimal rounding due to rounding. So if you multiply this by 3, and then you get this, and then if you multiply 0.619 by 3, it exceeds 1. This p-value is a probability, so can't exceed 1, so it will be replaced with 1. Okay. And Sidak's method, and you hand derive the p-value using a formula we saw in the lecture note, and Dunnett method, and we compare only 2 times. So you multiply this p-value by 2 instead of 3. Okay. So, so since we are actually we detected statistical significance with ANOVA, so you have an option not to adjust p-value for anything. Okay, so you may go with the p-value with LST, but if you worry about the reviewer and they still ask you to adjust for multiple comparisons, some reviewer do, and you may use the p-value based on Bonferroni or other method. So here's the interpretation of the result of one-way ANOVA. We see there is an overall significant difference among the mean and max FWT scores in the 3 groups. The p-value is 0.012. Therefore, we proceeded to look at difference between each pair of the group. We did not adjust for p-value for multiple comparisons because ANOVA test was significant. So I decided not to because ANOVA was significant. And the number of pairwise comparisons were relatively small, so it might be okay not to perform adjustment for p-value. We see that there is significant difference between the mean max FWT score for currently exposed group and the control group, with mean difference being 7.567 and 95% confidence interval 1.9 to 13.1. There is a strong trend towards significant difference between the previously exposed group and the control group, although this was not statistically significant. And there is no clear significant difference between the mean max scores for currently and previously exposed groups, and a p-value is 0.619, with the mean difference being 1.81. So based on this analysis, and what we detected is difference between not exposed to current and not exposed to past was had a trend but not statistically significant, and then current and past was not statistically significant. So that was the result of our analysis. Okay. And then let's talk about assumption of one-way ANOVA. One-way ANOVA is a form of linear regression, and we will study more on linear regression in the chapter of linear regression. Linear regression is a parametric model. What does it mean? A parametric model assumes normality in the residuals. Okay. And here, again, let's reserve the word residual for linear regression lecture. Here, you can see that as outcome. Okay, so outcome variable have to be normally distributed within each group. This is similar to student t-test. We examine normality in each group. Right? And the variances of outcome variables are the same across the group. Okay, but there is a test, and you can do to see 1, 2, and 3 are true. And then the last one, observations are independent to each other. So you can't have any repeated measures in the analysis. So the people who are in the group 1, 2, 3 have to be independent from each other. Okay. And so in order to know if we can use ANOVA, and we need to make sure our data fulfill these assumptions. And I know observations are independent and no repeats in the data set. And 2 and 3, and you could look at data distribution and judge, although there is a non-parametric options for ANOVA, so we can simply switch to non-parametric options. what is a nonparametric version of one-way ANOVA, which is Kruskal-Wallis test. Okay, so let's use Kruskal-Wallis test and see if the results are the same. Okay, so let's do Kruskal-Wallis test, and right. So you go to nonparametric and independent samples, and automatic compare distribution. Let's see, field setting, and you put max FWT in test field, okay, and then groups would be that type. Okay, and then setting. All right, let's see what automatic option does and run. So SPSS automatically picked Kruskal-Wallis test, and so this is a nonparametric version of one-way ANOVA. So null hypothesis is the same. We are checking distribution of finger wrist-tapping score is the same across all the category of lead exposure. Okay, and then its p-value was 0.007, is 0.007, which is significant. Therefore, you are allowed to look pairwise, post-hoc pairwise comparison. Okay, and unfortunately, nonparametric method does not give you pairwise what is analysis. What is a nonparametric version for student t-test, and that is Mann-Whitney U-test, and there is no Mann-Whitney U-test automatically came with this, so we have to go back and perform Mann-Whitney U-test. So go back, independent samples, and then field. I think when you click with setting, and then you can click Mann-Whitney U and 2 samples, and let's see what happened. Okay. All right, I was unable. Let's go to legacy. Okay, so go to 2 independent samples. Here you go. You put the max FWT under test variable, and you can put more than 1 outcomes here. And the grouping variable, you put the lead type, and here you can choose which 2 groups you want to compare. So I want to do 1 and 2. That would be control versus current. Continue, and OK. Right? So this is a p-value to compare control group versus current group. And we have to repeat this 2 more times for other pairwise comparison. So we go to, okay, let's do 1 and 3. That's the control versus past exposure, right, which is 0.059. And then you go back and do it again. Dependent sample. Okay. Oh, sorry. Go back. Nonparametric. Legacy. 2 independent. And click group 2 and 3. This will do current versus past. All right. The p-value is 0.682. So as you see, okay, this is a summary table. We did use Mann-Whitney U-test for nonparametric pairwise comparison, and so let's compare parametric version versus nonparametric version. As you see, the nonparametric p-values are slightly better with ANOVA and no exposure to current, and it's slightly worse for no exposure and current. No exposure to past and current to past. Okay, and since global test or ANOVA detected statistical significance, and you may ignore multiplicity issues or use 5% to judge statistical significance, or if you are more cautious, and you may go ahead to do Bonferroni, so use 5% divided by 3 as a new cutoff to claim statistical significance. Actually, let me fix this slide. This is parametric test. And global test is really ANOVA test. Okay. And what test? And we use Whitney for this. Okay. So when you do nonparametric analysis, you follow the same thing and we did in ANOVA. Perform the global test using Kruskal-Wallis test if it's significant, and go ahead to look at each pairwise. And I put the Dunn's procedure. Let me go ahead to fix this too. With Cox and Ransom test is same as Whitney. Okay, and then, or you can use Bonferroni or Sheffield's multiple comparison procedure, and if you want to go with more conservative approach. And if the global test, Kruskal-Wallis test, is not significant, then declare all distributions of outcomes are no different. So you finish your analysis there. So you can't look at each pairwise in this case.